Konnichiwa. Good morning, everybody. Je vais auprès de mes amis qui sont venus voir, ça va être beaucoup de maths, mais on aura le temps de discuter après. Okay, so I'm now starting to speak mathematics and music. And I was just on a coffee, and yesterday I was on a table, and a friend asked me, what's the relation between mathematics and music? And I asked him, what do you do? He said, computer science. So I asked him, what's the relation between computer and science? So we will start with the game I made here. And where is the presentation? Here. Oh, sorry. Let's start. Oh, this is a game. We are mathematicians. We are trying to solve problems with the help of mathematics and music. I will ask my girl, can you draw a line from this point to this point, but you must go only in this direction or this direction? Unlike in the Pac-Man, when you come here, you come back here, this place. So everybody understands this way to speak. That's the way normal people speak. And we, as a mathematician, I write it extra so you cannot read. We will say, can you find all Hamiltonian paths modulated from minor triads from F sharp minor to B minor, and you use only -1, -3 transposition. This is pure jargon, pure the way we speak. If you go and see a musician, he will say, you will ask him, oh, can you modulate from F minor to C minor, and then you can use only move to 1/3. You go to some mathematical guy, you will ask him, oh, can you find an Hamiltonian path in a circular graph that's non-weighted and that relationship to 0.9 and 11. That's 3 ways we will have the same problem. So mathematics and music is the same world we live in, but another way to describe it. That's the purpose of my talk today. Mathematics and music is a well-known society. We belong to American Mathematical Society. We have our Congress meeting every 2 years, once in Europe, once in the Americas, and we're going to meet in Singapore in, I think, in 2020. So we try to expand our society to the rest of the world, because it's not very well known, I think. Math musician, you all know math musician because you listen to MP3, you use networks, you can use the acoustic, you can use anything. So there are always mathematics behind the music. The part I'm working on, it's called musical structures. It is the way the music is organized, the way we put the notes together on the chords. We will come back on these notions later. And the musical structure, people working on canons, for instance, la 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 la. But it goes very far away. Like for instance, Johannes Sebastian Bach, Johnny Betch, he made a canon that works on a Möbius strip. So you can go very far with canon. My specialty is temperaments, harmonic structures, and what we see today is this harmonic path and progression, the way we go from one place to the other in a space that's maybe understandable to most part of the people. Now, for my friends non-mathematicians, you can get asleep. I'm going to talk very fast because this is pure mathematics right now. So, we are in Z12. I have 7 white and 5 blacks who are in Z12. In Z12, you can say this is a silo decomposition on Z12 is Z3 cross Z4. I will use a graph with a complex coloration of each node. The coloration is made by the complex number, which is represented by a shape and a color. 12 nodes, complex coloration. I used in my PhD the graph theory, and I construct the graphs called the planet graph as a Cartesian product of C3 and C4. So of course it's a Cayley graph. very fast on the process. Because it's a circular graph, you have the eigenvectors and roots are the root of unity. You can normalize the Laplacian and so on, until you have visualization. So this is a technique it's used in graph theory. You come from a pure combinatorial object, and you end up with an Euclidean structure, geometrical objects. That's what I used myself to demonstrate. Other people use some manifolds. Other people use some, what do they use, group theory or whatever. We all come to the same results. So I will use the quaternions to modulate. So why do I have a factor? Because I wanted to preserve, I see my friend from IRCAM, yes. We wanted to preserve the Euclidean distance. That's why I applied a factor on each quaternion. It's a couple of two orthogonal quaternions. So when I went to my mathematical teacher and I say, oh, Louis, it's strange because if I use geometry, I come to this. If I use graph, I come to this. Each quaternion is the same results. Is it normal? And he looked at me and he said, Gilles, if you found a difference, the mathematics would have would not be coherent. So it means that any way you took in mathematics, you can use it. So, as we say, tutti i cammini portano a Roma. So this was my clean space. If you came to my lecture, and I know some of my students are here, we are talking about some mathematicians. One was Euler. Problem we asked, that Euler asked the problem, can you go through each bridge once and come back? This is a graph problem. But Leonhard Euler was a mathematician. Leonhard Euler is at the beginning of what he called speculum musicum, and he wrote a lot of books in music. And while he was searching on graphs, he was searching for path on music. So Euler was writing musical chords while he was working on graph problems. We will introduce graph theory, and I will be finished with the pure mathematics. We will have some graph on dual graphs. That's it. Now, let's go for the movie. I really did appreciate the talk of Jean-Baptiste, the first one, when he talked about Fermat, and I realized when I saw he cited Mersenne, and personally I didn't know much about Mersenne, but the fact he was a great musician for us. Some people say Mersenne was the first mathematician. Some people would say it's Euler, some others would say Riemann, not your Riemann, but Hugo Riemann. And for me, the first mathematician was the guy who invented the cat flap. He was a great scientist in astronomy. He was great in chemistry. Do you know who it was? Any idea? Yes. He was the first guy to make relations between chromatism in colors and chromatism in music. At his time, we had only 7 notes, do, re, mi, fa, sol. So only build this circle. So now we can today extend the circle up to 12 tones. So this is the first mathematical object from circle to hypersphere. So we start with the circle. So I used the colors from Newton and I interpolated some to see. So, did I lost anybody? No. Okay, so let's go a little bit more. I will switch directly to my model. So we said I have 12 tones. I will split the tones 3 times 4 is 12. So I will attach a symbol to each note that I describe in my theory as a complex coloration on a graph, but you can say it's a shape and a color. That's what I use. And these are properties from the music. One builds a diminished chord for musician, and the other builds a plus chord. the 0 on the plus chord. Now this is 4D. Why it's 4D? We have each note has one form, one shape, and one color. So it must belong to one square and to one triangle. But it is impossible. It is impossible to do that in 3 dimensions. Like the same, if you have a 3D object, you have to rotate it to see it. So what I did with 4 dimensions is to replace 2 directions with 2 rotations. That has advantages to have more symmetries than you may have in a 3D Euclidean space, and you have the easier calculation with the quaternions. So how does it work? We will make it rotate on here the sounds from here. Okay, so you recognize when you have the here, you can say they are all space distance between these notes are 3 and 12. When you rotate in the other way, it's +4. Now I can combine rotations. And in this case, we will come back on this later. We will go through every note once. We describe what we call a geodesic. It's like a kind of equator on the sphere. And if I combine 2 rotations, +4 minus 3 is +1. So I get the chromatic circle. Let's say Newton said it, I'll be back. So Newton's back again here. You can project this or embed on a sphere. We get to some musical notions, what we call a chord. Well, you see, the numbers are the notes, and the letters are the chords. If we add 3 notes, Do, Sol, Mi, split the chords, that's called a C major, that's his name. Then I will change 1 note, the 7th become a 9. So the 2 chords have one difference, is 1 note is different from one part to the other. We only change 1 note. The term we use in math music is parsimonious voice leading. Just you imagine you have 3 singers and only one is changing at a time. So from this I can build a chord, but it's funny, it's an hexagon. Does it make sense? Would it be a composer who would use an hexagon? I don't know if it makes sense, if it's possible. Maybe we have the... Sure. So now I've made all these chords have this note together and they differ one from each other. Let's get around. 这是大哆的黑箱，这是小拉，这个是大fa. Donc on fait fa majeur, après on va passer fa mineur, la bémol, et do mineur. Et chaque accord ne diffère que d'une seule note. So when we went back on the circle, we went around this point. Of course, because I'm in 2 dimensions, to build my space, it's infinite. I can go this way or this way infinite. So for me, you can use it mathematically correct, but I cannot make a space to make people understand it and to have something with the whole symmetry. I just make the symmetry with the 4D. So on this space, I will put the notes, the major chords, and the minor chords. So, did everybody survive 4D on the chords? So we will now go to the point we will put the chords into the 4th dimension. We did exactly the same. You don't need to think it's 4D behind, because it just look this way and it's really logical. So I get back to my 4th note, Do, Sol, Mi, and I build the 1st chord. This is C major, and on the other side, so I will replace the number 4 by the number 3. It's like on the hexagon, but I do it on the sphere. if I wanted to represent everything, it's of course impossible to visualize that. So we have to put an artificial fog, like in London, so you can see only what's useless to us. So this is a visual object where I only see the part I am in space. And you will see I will rotate then the sphere to a different position. I will have three, because I was on hexagon in 2D, I will have three directions. So I can move from C major to E minor to C minor to A minor. And A minor. So that's, we say, ta do li xiao la hen ting. They are very, very related. Now you see on the top the hexagon, and then somebody's gonna kill me. We are rotating around one corner of the hypersphere. No, we're rotating around one axis going through the sphere. So it's like having the hexagon on a sphere. So what you can do in 2D, I can do it in 4D. Is everybody alive? It's great. So what to do with that? The goal of my talk on our presentation in general is to understand what the musician has in the brain, because he's doing mathematics, but he's not aware of that. Let's see something for our national anthem, made by Beethoven. This is just one part of Beethoven, just one harmonic progression. Beethoven's genius is not only that, he was master of symphony orchestration. But we do not pretend to reduce Beethoven to this part. We just explain the musical structures that's behind. Let's see it. You will have the 2 dimensions and the 4 dimensions. Okay, one again. So he was doing this pass by moving one note only. If you do this on a high sphere, it's a perfect rotation, and it's a perfect, of course, perfect. It's drawing a geodesic on here. So the answer to the question why he didn't finish here, because it was Beethoven. He has nothing to prove. And he said, if you start like this, everybody knows he was ending this way. A second reason, he doesn't need to do this, because musically, now he's being transposing, going to another chord from this, but through this space. Okay. Let's see some, now I have a lot of sample we can hear. We talk about Hamiltonian path. So when you guys go in Toulouse, you get out, you want to go to Saint-Pierre, you want to go to this pub, you want to see the doctor, you want to see the dentist, you want to pick up your children. What you do, in your head, you don't know it, but it's called a Hamiltonian path, so it's that you're going to each point. That's what we do, and that's what you heard yesterday. The music was composed by Moreno Andreatta, who is director of research at the French CNRS and at IRCAM, University of Strasbourg. We are working on applying some Hamiltonian paths. So I met a composer, it's Giovanni Albini. Che passa? Sorry. So, and now it's going very, very slow, and you will see I will change on each chord 3 notes, only 1 here. Each time I keep 2 notes. So if we go on the 4th dimension, on this side, it's very, very narrow move, because the chords are similar and they only differ from 1 tone. And Giovanni, he had he's an Italian composer, friend of us, is making what we call Hamiltonian path, so we will go through each chord once. Here. So I use 2 dimensions, because 2 dimensions you can recall the path. I use 4 dimensions because you have the aspect of symmetry. For us, we have 2 ways for visualization. It's going the 4D to have the symmetry and the 2D to have to recall the path, and you will see, as Beethoven did, Giovanni went through every chord here. This one is 1 minute. The question I asked you at the beginning, how can I do it? Go through each chord one and only once. Here is a solution, graphical solution. So we use the same hypersphere, but we draw other relationships on here. So we are really trying to go here by only using this direction and these directions. You can solve it, we have solved it with music. A friend of us solved it with group theory, or whatever you need, or with computer. And then he finished, returns home. So it could be seen as a challenge for a musician, make me a Hamiltonian path. It could be a method, a technique to create music, but we use it a way to analyze. And I will answer the last question we had. Which composer may have made for me, one of the greatest composer? I will show you here. Now, this is a concrete application, what we use when we teach music, when we go to conservatory, to explain the path we found in the music. We found a lot of paths in Paolo Conte, Michel Legrand, anybody you need, jazz musician. Here, we're going to use from Wagner. So what you see in the center, this is what we call the tonal center. So the spider will come back always to the center. It's another concept we've developed as well. But what we want to show with this, that in 2 dimensions, you see that he's coming back to the center. So there are a lot of advantages with 2 dimensions. If we do the same in 4 dimensions, of course, you don't go from one side and come back from the other, but you stay on a sphere. There are other mathematicians working with 4 dimensions, but they plunge into the come si dice, in the center of the. It's very hard for a human to move in 4 dimensions. That's why I put my 4 dimension rotating in front of you. And this is the last answer to the question, who could have made an hexagon? So here I show it in 4D. Okay, I put it here. Okay, so that's what Wagner did. I've tried at home. It doesn't sound like Wagner, because music is not only harmonic path. Music has a background, has auditorium, has Klangfarbe, has spatialization, and you can repeat it. You can use the same grid of chords. One will be Daft Punk, the other will be unknown. One will be Beethoven, the other will be unknown. So we study musical structure, and the goal is to reinforce impression that you have with audition, with visual support. Okay, that was it for today.
Thank you very much.
Thank you. Arigato.